Captions in English, please. So this is the first video of Chapter 9. Chapter 9 is on chemical quantities, and this first video will focus on mole-to-mole conversions. So what do the coefficients in a chemical reaction mean? For example, if you have 2 H2 gas plus 1 O2 gas gives 2 H2O gas, what the 2, the 1s, and the 2, the ones are usually implied, but what do they mean, those coefficients that are in front of the formulas of the molecules? They mean that 2 molecules of hydrogen gas react with 1 molecule of oxygen gas to produce 2 molecules of water vapor in this given chemical equation. But because we don't usually deal with molecules because it's impossible to deal with just a few numbers of molecules, instead we are talking in moles. So we multiply the number of molecules by the Avogadro number, and then it becomes 2 moles of hydrogen gas react with 1 mole of oxygen gas to produce 2 moles of water vapor. So that's how you want to read those coefficients. So let's consider the combustion of octane, C8H18, a component of gasoline. So if we look at its chemical reaction of combustion, it's 2 molecules of octane, C8H18, liquid, plus 25 O2 gas will produce 16 molecules of CO2 gas plus 18 molecules of H2O gas. So the balanced chemical equation shows that 16 moles of CO2 are produced for every 2 moles of octane burned. And you can see that this is due to the fact that there is 8 carbon in the octane. And so you make a molecule of carbon dioxide for every carbon. And because you have 2 moles of octane, you get 2 times 8, 16 moles of carbon dioxide whenever you burn 2 moles of octane. Since we know the world's annual fossil fuel consumption, we can estimate the world's annual CO2 production using the balanced chemical equation. And so calculations shows that the world's annual CO2 production from fossil fuel combustion matches the measured annual atmospheric CO2 increase, implying that fossil fuel combustion is indeed responsible for increased atmospheric CO2 levels. Because, let's just emphasize here that fossil fuels are, anything that is found in the ground that is made of carbon, hydrogen, and oxygen. And whenever we burn those fossil fuel, we are producing carbon dioxide and water. That's always the case when you're burning compounds that contain carbon, hydrogen, and oxygen. And so we're producing a lot of carbon dioxide and water vapor. Whenever we burn, let's say, gasoline, kerosene in plane, natural gas in our houses, coal in power plants. So all these fossil fuels that we burn are releasing carbon dioxide and water in the atmosphere. And so calculations have shown that the world annual CO2 production from fossil fuel combustion matches the measured annual atmospheric CO2 increase. So there is proof that the fossil fuel combustion is indeed responsible for increased atmospheric CO2 levels. So the numerical relationship between chemical quantities in a balanced chemical equation is called reaction stoichiometry. So this is a word here that means any kind of calculations that involves the use of the coefficient of a chemical, of a balanced chemical equation will be called like that, stoichiometry. And so using the balanced chemical equation, we can predict the amount of products that form in a chemical reaction based on the amount of reactants. You can predict how much of the reactants are necessary to form a given amount of product. And you can predict how much of one reactant is required to completely react with another reactant. So all combinations are possible here. Whenever they are part of the chemical equation, you can use the proportions to find the amount of one reactant versus another reactant, or a product versus a reactant, etc. So all these calculations are named stoichiometry. So to understand how we do this, let's go through an analogy from a kitchen recipe. So a kitchen recipe gives numerical relationships between the ingredients and the number of pancakes, in this case, that you can make. So to make pancakes, you need the flour. So 1 cup of flour with 2 eggs and half a teaspoon of baking powder will allow you to make 5 pancakes. I believe it's missing the milk here, but it doesn't matter. You only look at certain ingredients here. And so you can make 5 pancakes with 2 eggs or 1 cup of flour. So this gives you numerical relationships between how much of the ingredients you need to make a given, not a given, but a wanted amount of pancakes. And so if you have 2 eggs only, for example, you know that you can make only 5 pancakes. If you have enough of everything else, the eggs will limit the number of pancakes to 5. And so there is this relationship between the eggs and the pancake that you can use to convert. And you can write this relationship as a ratio, as a conversion factor, where you have, for example, 2 eggs over 5 pancakes, or 5 pancakes over 2 eggs. And so these two ratios can be used as conversion factors between pancakes and eggs, depending on what you start with. For example, if you have 8 eggs and you want to do as much pancakes as you can from your number of eggs, given that you have everything else in enough quantity. So your given amount here would be 8 eggs, and you would multiply by the ratio that has the 5 pancakes on top and the 2 eggs on the bottom, because this way eggs cancel, the units of eggs cancel, and you do 8 times 5 is 40, divided by 2 is 20. So you can make 20 pancakes from 8 eggs. And so it's the relationship that was saying that 2 eggs will lead you to 5 pancakes that can be used as a conversion factor. And so it's the same in chemistry. In chemistry, you can use the chemical equations as recipes. The chemical equations give you proportions of the reactant that will react together and how much of the product you can make. So in a balanced chemical equation, we have a recipe for how reactants react or combine to form product. So this following equation shows you how hydrogen and nitrogen combine to form ammonia. So it's like a recipe. It's used, for example, in the industry to make, products. And so here it shows that 3 molecules of H2 react with 1 molecule of N2 to form 2 molecules of NH3. Remember how NH3 is called ammonia? So from 3 hydrogen molecules reacting with 1 nitrogen molecule, you can form 2 ammonia molecules. It's given by the chemical equations, those proportions. The coefficients are your proportions. We can express these relationships as ratios. So, for example, 3 H2 molecules is equivalent to or will react with 1 N2 molecule, and that will lead to 2 molecules of ammonia. So those columns here are like your equivalence symbol. Since we do not ordinarily deal with individual molecules, we can express the same ratios in moles. So 3 moles of H2 will be necessary to react with 1 mole of N2 to make 2 moles of NH3. So all of these are equivalences that you can use. And so we can write a relationship or a conversion factor between each compound in the reaction. And these are called mole ratios. These were called mole ratios. So from the mole ratio between hydrogen and nitrogen that says we have 3 moles of hydrogen reacting with 1 mole of nitrogen. You know, here we use the equal sign. Of course, it's not an equal, that means they are exactly the same. It just means it's the proportions you need for them to react together in this particular equation. And so because mathematically we can write this as an equality, then we can write conversion factors, 2 conversion factors per equality. And so the 3 moles of H2 equals 1 mole of N2 can be written in ratios as 3 moles of H2 over 1 mole of N2, or 1 mole of N2 over 3 moles of H2. Same with the equality between the moles of hydrogen and the moles of ammonia. There is 3 moles of hydrogen needed to make 2 moles of ammonia. And so you can write 2 conversion factors from this. And same with the relationship between nitrogen and ammonia. 1 mole of nitrogen will allow you to make 2 moles of ammonia. And so you can write 2 conversion factors from this. So we call these conversion factors mole ratios, but there are conversion factors, you know, between moles of one kind of molecule to moles of another kind of molecule. So that's why they are called mole ratios. They allow you to do mole to mole conversions. So let's go through an example, still using the synthesis of ammonia. So if we have 3 moles of N2 and more than enough H2, how many moles of NH3 can we make? So here the concept map will show what we start with. And here we start with 3 moles of N2 and we want to find moles of NH3. So from moles of N2, we want to find how many moles of NH3 we will make from 3 moles of N2. So you use the equation to find the relationship between the moles of nitrogen and the moles of ammonia. And here 1 mole of nitrogen allows you to make 2 moles of ammonia. That's from the balanced chemical equation. So change that into a conversion factor. And because we start with moles of N2, we want the mole of N2 in the bottom of the in the bottom of the conversion factor. So 2 moles of ammonia over 1 mole of nitrogen. So when you're ready to do the calculation, you take the given amount of 3 moles of N2 and you multiply it by the conversion factor, that is 2 moles of ammonia over 1 mole of nitrogen. This way the moles of nitrogen cancel. And here notice how it is very, very important that you specify moles of what? Moles of nitrogen here cancels. And you're left with moles of ammonia. If you are not careful by not writing those, you know, which species it is, it's going to be impossible to solve those problems. It is very important that you are thoroughly writing everything. So here it comes down to multiply 3 times 2, and it's 6 moles of ammonia from 3 moles of nitrogen. And that makes sense because you double the amount of molecules of ammonia from 1 mole of nitrogen. Let's look at a second example. If we have 5.5 moles of hydrogen, how many moles of nitrogen is required to completely react with the hydrogen gas? So this time we have moles of hydrogen and we want to find moles of nitrogen we need to react completely with the hydrogen. So here we are dealing with the 2 reactants. So from the chemical equation, we see that 3 moles of hydrogen are reacting with 1 mole of nitrogen. That's the coefficients in front of H2 and N2. So from this equality, we can write a conversion factor. And because we start with moles of hydrogen, We want the 3 moles of hydrogen on the bottom of the conversion factor and then the 1 mole of nitrogen on top. So when we are ready to do the calculation, we take the given amount of 5.5 moles of hydrogen and we multiply it by the conversion factor, which is 1 mole of nitrogen over 3 moles of hydrogen. We see that the moles of hydrogen cancel, and again, it is important to specify moles of what. Here it's mole of hydrogen that cancel, and we're left with moles of nitrogen, which is what we want to find. And so 5.5 divided by 3 is 1.8 moles of nitrogen that you can make from that you will need to have to completely react with the 5.5 moles of hydrogen. Let's go through a concept check. So again, you want to pause the video and work this out on your own before you watch the answer so that you can learn to do it. So we have cobalt reacts with fluorine gas to form cobalt-3 fluoride in the following unbalanced reaction. So it shows how cobalt, the solid metal, react with the fluorine gas F2. So F2 is one of those diatomic molecules from, in their elemental state, they are diatomic molecules made of 2 atoms of the same kind. And you're forming cobalt-3 fluoride. So you have 3 fluorine for 1 cobalt in this compound, and it's a solid. So we have 2 questions, and let's start with question A. But before we can do anything here, notice how the equation is unbalanced, which means we need to first balance the equation, because right now it doesn't give us the right proportions in which they will react. It's not correct. So let's balance it. So count the number of cobalt on both sides, and there is 1 cobalt on each side. Fluorine, there is 2 fluorine on the left and 3 fluorine on the right. So we need to balance the fluorine. And when you have 2 and 3 on the different sides, the best way to balance is to make it 6 on both sides. So we will need to multiply by 3 on the left to make it 6, and by 2 on the right to make it 6. So the coefficient of 3 will go in front of F2 on the left, so that 3 fluorine times 2 fluorine per molecule of fluorine, that's going to be 6 fluorine. And then the coefficient of 2 will go in front of COF3, and then the subscript 3 for fluorine will multiply the coefficient 2, and that's going to be 6 fluorine. But we have unbalanced the cobalt by having the coefficient 2 in front of COF3. Now we have 2 cobalt on the right. So we need to make it 2 cobalt on the left by multiplying by 2 in front of CO. So that's going to be the final balanced equation now. 2 cobalt will react with 3 fluorine gas to make 2 molecules of COF3 solid. So COF3 is actually an ionic compound, so we would say 2 formula units of COF3 and not molecules. So now we can answer question A. If 4.2 moles of fluorine gas and enough cobalt is used, how many moles of cobalt-3 fluoride can be produced? So the concept map will show what we start with. And here we're starting with moles of fluorine gas, 4.2 moles of fluorine gas. And we want to find moles of cobalt-3 fluoride. So moles of COF3. So it's a mole-to-mole question. So we need the mole ratio here. And using the balanced equation, we can see that 3 moles of F2 will react with 2 moles, will produce 2 moles of COF3. So this is obtained from the balanced equation here. It's the coefficients in green. So using this equality, we can write the conversion factor. And since we start with moles of F2, we want to have the moles of F2 in the denominator of the conversion factor. So it's going to be used as 2 moles of COF3 over 3 moles of F2. Now, to do the calculation, we start with the given amount of 4.2 moles of fluorine gas, multiplied by the conversion factor, which is 2 moles of COF3 over 3 moles of F2. And the moles of F2 cancels, and we're left with moles of cobalt fluoride, cobalt 3 fluoride. You do 4.2 times 2 divided by 3, and it's 2.8 moles of cobalt 3 fluoride. So this way we could calculate the number of moles of cobalt 3 fluoride that can be produced from 4.2 moles of fluorine gas. Let's look at the second question, B. If 2.5 moles of cobalt is used, how many moles of fluorine gas is required to completely react with the cobalt? So the concept map will look like this. We start with moles of cobalt, 2.5, and we want to find how many moles of fluorine gas. So from moles of cobalt to moles of fluorine gas that are needed to completely react with the cobalt. So these are the two reactants. So we look at the balanced equation to find the equality between these two. And we find that 2 moles of CO, the cobalt, so the 2 comes from the coefficient in front of CO, equals 3 moles of F2. The 3 comes from the coefficient 3 in front of F2. So written as a conversion factor, it will be 3 moles of F2 over 2 moles of CO, because we start with moles of CO. So we want to cancel the units of moles of CO. So we want the moles of CO in the denominator of the conversion factor. When we are ready to do the calculation, we will take our given amount of 2.5 moles of cobalt and multiply by the conversion factors, which is 3 moles of F2 over 2 moles of CO. We can see that the moles of CO cancel, which is what we want, because we are left with moles of F2, and that's what we're trying to find. In the calculator, you do 2.5 times 3 divided by 2, and it's 3.75 moles of F2. However, here, the given amount had only two sig figs, 2 and 0.5. So here we need to keep two sig figs only, and so we will keep the 3 and the 7. What comes after the 7 is a 5, so you need to round the 7 up to an 8. And the final answer will be 3.8 moles of F2. So that's the amount of fluorine gas that you need to bring to completely react with the 2.5 moles of cobalt.